I need to record this for posterity. I don't want to see me on videotape.
The world famous.
We're all famous, yeah. So, well, I'm Lynd Bacon. I'm sort of primarily an applied quantitative methods person. I do most of my work in the area of marketing science. Most of my training is in areas like econometrics, psychometrics, and machine learning. So I'm not like a legitimate statistician, although I've had a certain amount of coursework and some decades of experience in applications, and I do a little teaching periodically on the side. Currently, I'm teaching a graduate program from Northwestern on a distance basis. So that allows me to avoid going to Chicago in the winter, which I think actually they just had frost this morning up there. So I kind of gloated this morning in my faculty. But what I'm going to talk about today is doing Bayesian statistics in R. And this may be new to you in at least two respects, depending on your background. You may be unfamiliar with Bayesian statistics, you may be unfamiliar with R, or you may be unfamiliar with both. Or you may be unfamiliar with some of the application that I'll talk about, which is all fine. But not knowing anything about it, I tried to pick sort of the right middle of the road to that. To me, it's a compromise that's not going to satisfy anyone. So, but it's Friday afternoon, and I appreciate you being here. I also realized after I pulled some slides together for this that I probably didn't have enough jokes given that it's Friday afternoon as well. If you'll bear with me, I'll periodically put in one or two. So I probably should have basically introduced myself as a reformed frequent statistician. Although my Bayesian roots go back about 3 decades at the University of Chicago, which is where I first got baptized into the Bayesian world. And it's gotten a lot less crazy and maybe more popular since then. My knowledge is definitely skewed in particular areas. So, like I said, I'm not like a legitimate statistician. I'm not a math stat person. I've basically learned things that I've had to learn either because I'm teaching them or because I needed to use them. So I've been fairly eclectic in my approach to things. So what I'm going to talk about is Bayesian statistics in R. I'm going to talk a bit about why would you use R for this. And I'll also give you some reasons why you might do it at all, why you might be interested in this way of thinking about statistics. I'm going to talk about a class of methodology that, by and large, much most applied and theoretical work is done with these days, and that's with simulation methods, Markov chain line Carl simulation methods, which are really indispensable for solving the kinds of difficult estimation problems that we deal with. And I'm going to finalize by talking about an application in the area of measuring the structure of preferences using data from a technique that's called choice-based conjoint measurement. And I'll tell you a bit about that, so it's not so mysterious. But it's actually very, very broadly used. Okay. Then if you have questions, jump right in.
Are your slides online anywhere?
I will post them online, or maybe I'll pass them to one of you guys.
I'll put them on GitHub.
That way we can revise them as we go. I'm sure there's going to be some errors in here. There's always something when I look at my slides and go, crap, that equation's wrong. Hope nobody notices.
Okay,
So,
we have a link on our Meetup website for the GitHub.
I'll put it up there again.
Yeah, right on the front page so
Okay.
that people will miss it.
I guess we can add it, like details probably, right?
I don't know. Yeah. But that would be good, right?
We'll definitely do it.
Who's never seen this demo? Has everybody ever seen this somewhere in your education, or you know what that is? Who's never heard of Thomas Bayes? Has everybody heard of Thomas Bayes? You know who he was? How long ago he lived? What he did for a living? You're shaking your head. You don't know
I
about
don't know the details. I have heard the name a lot, but I don't know.
I've always been suspicious because in the Northeast there's been branded English muffins called Thomas's and Bayes. I never figured that out. But that's not the same Thomas Bayes, I don't think. Thomas Bayes was a clergyman who lived in the 18th century. He was also a member of the Royal Society of London. So he's also considered to be a scientist. It wasn't unusual, back in the day, in that day. Oftentimes, for scientists to earn their keep, they had to have roles in the church. Some had to be astrologers. I think Kepler was the court astrologer. The astronomer Kepler. But he told people horoscopes. That's how he got paid. Well, people who worked in the church, you were basically educated either if you're in the clergy or you did something like some kind of science, mostly physicians. So Thomas Bayes basically wrote a lot about probability. But it wasn't until after his death that a colleague of his, Richard Price, actually presented the work that we know today. it's Bayes' theorem. And this is what it is. I'll tell you what this is in a minute. Price presented a talk to the Royal Society about a year after Bayes' death in 1762 or 63. And then, in keeping with the custom of the day, he then basically submitted a paper that was his presentation. And that's the paper that you can find online. And it's sort of an interesting read. But Bayes never wrote this equation. But here's what it is. You know, in the simple case where we have events A and B, that there's some uncertainty about the occurrence of it, what this equation says is that the probability of observing event A, given that B occurs, is equal to, in the numerator here, the probability that B occurs given that A occurs times the probability of A divided by the probability of B. This is what's known as Bayes' theorem. And it's actually very easily derived from just the basic rules of conditional probabilities. Bayes never wrote it down. But Price, I guess, was listening to him and he wrote it down. And we probably don't need to go through this because this is just a simple derivation. So at the very top of equation 1, we have just the basic rule of conditional probabilities, the probability of D. Probability in the dark. Okay. Conditional on the occurrence of A is equal to the joint probability of B and A occurring divided by A. And it turns out if you just do a little simple algebra and take advantage of symmetry in these relationships, you can get two different versions of the Bayes theorem. It's very handy equation. Much of what we do today is sort of based on elaborations on it. Anyway, that's who Bayes was. No one, by the way, as far as I can tell, no one knows what he really looked like. There's all these pictures of a guy with like a, you know, some kind of cleric's collar or something, but nobody really knows. Now, the way that we often write it when we talk about fancy-dancy models is we write it this way. And we put in some Greek characters because it makes it look more scientific. Right? But basically, this is the same statement here, although instead what we've done is we basically identified a set of parameters whose posterior distributions we want to identify, represented by the thetas. The D is data that we've observed. So on the left-hand side, what we have is the joint posterior conditional probability distribution of the parameters theta is equal to what's on the right-hand side of that equation. So just the common terminology is what's on the left-hand side is the posterior distribution of theta. And of course, for interesting problems these days, that's a very high-dimensional joint distribution, 3,000 dimensions. Therein lies the challenge in estimating these things. L is basically the likelihood of the data given the values of theta. P theta is just the prior distribution of theta, and PD is just the density of the data. It's a constant, right? So because that's a constant in the denominator, it allows us to take advantage of a very convenient proportionality, and that's down here at the bottom. And most of the approaches that we use to estimate the posterior distributions of these thetas take advantage of this proportionality. We can ignore that denominator. Okay, so far. Getting more scientific. Get a few more Greek letters in there. But before we get to that, it's reasonable to ask why it is that people use Bayesian statistics at all. Certainly it hasn't always been very popular. It's been the cause of some rancor and a certain amount of suspicion on the part of the traditional statistics community. But there's a variety of reasons that Bayesians give. One is, although this is not always viewed as a benefit by all, and that's that you can incorporate prior knowledge in your estimations. That's what those priors are. They're your best guess at the distribution of those parameters before you observe data. So that's either good or bad. My experience, anecdotal experience with decision makers like managers, they kind of like that idea. They don't understand why. But it makes sense to them that somehow they should take advantage of what they've already learned. Then they get data, and then they update what they learned. Bayesian estimators are shrinkage estimators, and that means that actually they're less vulnerable to random variation and inflating causing bias in the values that algorithms converge to when estimating them. When you use Bayesian statistics, you can avoid using asymptotics. So you don't have to make assumptions about what happens with a statistical estimator as your sample goes to infinity, an asymptotic estimator. You just basically deal with the results that you kind of have. You can avoid now what's the increasingly disrespected null hypothesis statistical testing procedure. There's a lot of literature recently I think the last time I was here 2 months ago, we talked a little bit about that, the current kerfuffle about that. What's that journal? Basic and Applied Social Psychology, where the editorial board just decided no more of this stuff. Right now, their solution doesn't seem to be great, and so some people I know actually have written the editorial board saying, well, you know, don't throw the baby out with the bathwater here. But anyway, there's some problems with it, and if you read people, statisticians like Andy Gelman, he's got a great blog he talks about this. There are other people who talk about it too. One of the other advantages in using these techniques, and in particular taking advantage of certain modern architectures, is that we can exploit with what we refer to as information pooling, where we take advantage of the similarity between units to overcome certain problems with sparse data. And the example I'll give towards the end of our time together, you'll see how that's done explicitly for that particular type of model. We can estimate models that are not amenable to closed form solutions. The whole origin of the current practice was in solving very, very difficult physics problems in the Manhattan Project. So back when much of the work that had been done was declassified, it was published by people like Metropolis and Teller. And a lot of the early contributions to Bayesian thinking as we know it today was in the field of physics, not in biostatistics, not in social science, etc. Because if you think about the problems they're trying to solve in the Manhattan Project, they were incredibly gnarly, to use the right technical term. They were trying to solve integral calculus problems in thousands of dimensions. And how would you do this? You could never solve these problems analytically. So instead, what they came up with was a series of methodologies that allow them to approximate those densities in high dimensions by step-by-step sampling, taking conditional random draws from each marginal distribution and then putting it all together again. And that's basically how most of the algorithms we use for doing simulation-based Bayesian estimation work today. It's the same approach, except in those days they just had rooms full of physicists with adding machines. And that's how they did it. I mean, just an incredible task of organizing the activities of all these people, mostly guys with ties, right? Sitting in a room with like Monroe hand calculators, and somebody keeping track of how it is that they were passing information from one iteration of the algorithm to the next. So it probably took a few years to do that. It didn't necessarily end up in the best product, that's for sure. But so anyway, that's another reason why Bayesians will say we use some of these techniques. Another benefit is that these methods provide kind of a natural way of treating missing values. Because in a sense, all the parameters we estimate are missing values. So if you have a missing data point, you just sort of estimate it in the same way. Because that's what we're doing. We're making inferences about things we couldn't observe directly. We put distributions on things. We turn the crank of these estimators, and then we get a prediction of what that thing would have been. So that's very nice. And then finally, and this one also kind of raises the hair on the back of some people's neck, but using these simulation methods, we can get arbitrarily precise estimates. Because it's now not a matter of the sample size we've got, it's a matter of how long we run the algorithms. So the longer we run, the closer we get to really being accurately representing the posterior distribution of some parameter. Now, it's a matter of diminishing returns, not surprising. So the precision increases proportional with the square root of R, or the number of iterations we're running, just like standard deviation decreases, right? But the point is, we may have a finite set of observations of data that we've observed, but the parameters of the models that we use to summarize those data, we can estimate by just running very, very long numbers of iterations. They're called chains, sampler chains, and getting more and more precise in our approximation of the distribution of the posterior distribution of those parameters. So those are what Bayesian is. Now, not surprisingly, there's some negatives to all this. One is, well, geez, you have to write full probability models for everything. So the math gets a little bit more demanding because you've got to incorporate the priors, and then ideally there's certain sets of priors that are easier to use than others. I won't spend a lot of time on that today, but there's some that work that others don't work, and you have to be sort of picky about that. And those are the dreadful priors that people refer to as articles published in the last 5 years, where that was actually part of the title, the dreadful priors, because you have to come up with priors. But it turns out in practice, in particular areas, there's enough accumulated knowledge, at least you get a sense of what everybody else is using, and either you're all wrong or maybe you're all on the same page. But it's a little bit easier than just sort of making up things around. So there's priors on the prior.
There's always the non-informative prior.
There's always a non-informative prior. That's right, or it's basically kind of like a flat prior. Now, ideally, priors are proper priors, right? So, you know, what that means is that it has a finite interval. Obviously, if you go back to the equation, you multiply something that has an infinite area underneath it, it's not going to help you posterior. But, yeah, in fact, non-informative or weakly informative priors are often used to basically read priors for things like variances, for example, depending on, you know, how your algorithms work. Computational intensity is a big drawback, or it is currently, although there's been a lot of advances in recent years on approximations and on making these algorithms run in a more parallel way. There are certain challenges in making them parallel because of the way they share information from one iteration to the next, and the way that parameters depend on other parameters. Because parameters have parameters in these models, they have hyperparameters. Results overload is another one. This actually, a lot of the work that I do is kind of a challenge for the recipients of some of the work, because in fact you get, you know, if you have a model that's producing, say, posterior distribution information on 4,000 parameters, and they'll have something to do with something like people's product preferences. You have to summarize that somehow for decision makers. And so you're always walking this line between making it as simple as possible for them, but somehow not allowing them to completely disregard uncertainty of things. So as Ed Deming once said, to paraphrase actually, the fundamental task of managers is to understand variability, right? So you want to kind of guide decision maker to use the information as best as possible, but you can't just like overload it. In fact, for the analyst, there can be a lot of overload too. So it's a good idea to have some pretty good analytic plan before you go into it and use all the information that's available when you run these simulations. Excuse me. And finally, explaining Bayesian inference to non-Bayesian. And this is a whole other kind of can of worms. But in fact, it's probably easier to explain it to non-statisticians than it is to explain it to non-Bayesian statisticians, because there's a certain amount of fervor around the issue. And if you're an academic, it can be a challenge also with basically using Bayesian techniques to submit to a journal where they can't find a reviewer, for example, to basically properly appreciate your methodology can be a real problem. In the world of decision support, though, it's a little bit different, because oftentimes we hide much of this stuff from clients unless they're particularly adept at these things. Another one on here, that it used to be the case that if you were Bayesian, you were considered to be like a cult member. And Bayesians didn't really help themselves that much in that regard, because they used to write their own special songs. They had rock bands at their conferences. They had Bayesian rock music, you know. I mean, it was pretty crazy. So, you know, the group at that time, some decades ago, probably at least partly deserved the reputation. And they were also not necessarily as diplomatic in their criticism of non-Bayesian statisticians. But like I said, I tend to look at these things from a very collective perspective. I basically use tools that work, and oftentimes these tools work for me. Although sometimes not without a little bit of pain. Okay, so what about Bayes and R? Well, there's a lot of reasons that you do Bayesian statistics in R. Many of them are kind of more general reasons why you do any kind of statistics in R. R is a very powerful programming environment. It has a very, very large array of packages. If you haven't looked at that, here, just take a look. See if I can find it. Is it going to show? Yeah. Oh, okay. So in the R mirrors, there are these things called task views. I can't actually show you the whole one. The task views are kind of moderated or maintained by a maintainer, and they keep track of all the different packages to have algorithms and tools for particular types of statistical applications. This is the one for Bayesian methodology, and it's very large. There's a whole variety of different techniques in here. These are all packages that people have written. They're more or less tested and usually correct, maybe not always. Here they are. I won't go through all these because we don't have that much time, obviously. But I can tell you that there's some general classes that are worth paying attention to. So there's packages that do Bayesian parametric statistics, which is most of what I'm talking about today. But there's also semi-parametric Bayes methods, and there's non-parametric Bayes methods, and they vary a little bit in their flavor depending on the area of application and who has been developing them. There's applications that are specifically developed for use in the social sciences, from biostatistics, which you're probably aware of, and in econometrics and in machine learning. Machine learning applications include things like Bayesian tree models, They're kind of sort of a Bayesian version of CART models, Bayesian model averaging, tools like that, that machine learning people have become particularly favorable. You probably know this, but the standard or baseline technique for doing document classification is an IU-based classifier, right? It's not really true Bayes, as a Bayesian we talked about it. And another very popular technique in machine learning these days is Bayesian belief networks. Right? It's also, again, sort of not true Bayes in the sense we're not working out this full probability model, but they're definitely Bayesian applications. So it's kind of all over the place. I've heard it rumored that, in fact, that very irritating helper paperclip they used to pervade Microsoft Office was also a Bayesian application. And it was learning to be irritated, apparently. Because there's a lot of stuff online about how to get rid of this thing, you know. But anyway, and there's also packages for learning or teaching Bayes increasingly. One of the ones that I particularly like is Jim Albert's Learn Bayes package. There's a Springer population that goes with it out of the useR series. And the code for these things are available. It's actually it's something I recommend to students when to kind of get them to the place where we're going to actually do real modeling. The R language is also convenient for rapidly prototyping things. So it's not unusual that you might try to implement a new algorithm in R and then find, geez, you know, I just can't wait for this thing to finish. So you might decide that basically to up the ante and code it to something like C or Fortran and then call it from within R. That's not unusual. A lot of the packages do that, particularly the ones that do Markov chain like Carlos has done. R has very superior methods for graphics and data visualization, which is now sort of at the heart of ours. It came from S, from Bell Labs. It has packages that, like Lattice, which came out of the Trellis package in S, ggplot2, which is based on Wilkinson's grammar of graphics, and a variety of things that make it easier to actually try to visualize the results you're getting out of models that are kind of very large parameter space models like these. And then, as I kind of mentioned, some of the computation makes more sense to do outside, and R makes it possible to access algorithms or sampling engines for Monte Carlo simulation in other environments. So in particular, the environments include Bayes updating with Gibbs sampler is actually kind of an R public domain version of a platform that was originally developed at Cambridge. Just another Gibbs sampler, Mark Plummer package. Stan, which is from Andy Gelman and his colleagues at Columbia. And then, of course, you can write code in other languages, increasingly even in scripting languages like Python, and I expect to see something in Julius as you call. So if you find you can't get enough velocity out of however it is you coded in R, and you don't have the opportunity to take advantage of parallelization of your code, then in fact, the next strategy is to kind of move to something that's going to execute faster, take advantage of R's ability to manage the data, to publish results, and so on, and to set up a run, submit to an algorithm that's running outside of the R environment that is called, and so on. And finally, R, of course, has nice tools for accessing databases and proprietary data files that come from different systems. Maybe not as much as some other packages, but it's definitely in there. I don't actually use a lot of proprietary data formats, so I'm not really up to speed on kind of what to tell them. And finally, last but not least, as you know, there's a very, very large and active developer and user global community for R, which is a lot of where kind of the real value and power is coming from in this environment. It's kind of like Linux, right? Or Python. And so that's a real advantage. Chances are that whatever it is you're trying to do, somebody has probably done it. And if you're a believer in not reinventing the wheel like I am, the first thing I'll do is I actually look for examples online. And it's true with graphics too, right? You know, if you want to figure out how to write the code for graphics, you look for some example somewhere. You look in a library. If you want to know how to do a widget, you look for an example. And so that's what's really very different than not many decades ago. You know, we didn't have the ability to basically search the internet and look for solutions to problems that we thought we'd have to like go to the library and figure out. So anyway, those are a number of reasons why we would do Bayes and R. I mentioned that these methods, when simulation techniques are used, are very computationally intensive, and that's often one of the challenges in R. R is not the quickest tool in the shed, and also it stores results in RAM. So there's certain constraints on how much you can do at any given time. One thing you learn in regard to ladder is save early and often when you're running in sessions, because you know, if you have a power outage or something like that, if you haven't saved the content of your session save that image, open close parent. You're going to be, sorry. But anyway, by and large, despite the kind of constraints, there's been a considerable growth in tools for doing Markov chain Monte Carlo estimation, Bayesian hierarchical-based models in particular. By taking advantage of the ability to call code that's written in some compiled language you call from outside and so on. And that's good because this is basically, these are the techniques we use to estimate the parameters of really interesting and useful models. The class of simulation techniques in general is referred to as Markov chain Monte Carlo simulation, and for obvious reasons. At least it's a name that means something, right? So it's Monte Carlo simulation because we're making some draws from some distribution. It's a Markov process because the draws are conditional on the previous iterations set values that we're drawing. So it's Markov chain Monte Carlo estimation. The samples that we draw over successive iterations are referred to in the vernacular as chains. So you have, for each parameter, you can have a chain that you generated by successive iterations through the algorithm. And that chain actually, once it's met your requirements for stationarity, if you will, actually allows you to use the data points that are generated after getting rid of those that have been prior to the thing stabilizing to make inferences about the distribution of that parameter. I'm going to give you some examples of this. And there are several different flavors of this kind of sampling algorithm depending on the parameter of interest and some other constraints. All right. Any questions so far? Going too fast? Too slow? Not Joe. Okay. There's more and more Markov chain sampling algorithms all the time, but these are kind of the classic ones, and they're basically distinguished by one important difference. Actually the simplest one, and I'll show you a very, very simple example of how this works in a minute, is referred to as a Gibbs sampler. For the life of me, I don't know why it's called Gibbs. Somebody knows that. I keep forgetting to look that up. But it was actually described initially in the early 80s. And then it was actually sort of additional interest in it was stimulated by this paper by Galbraith and Smith in 1990. And basically, the idea is basically this, that rather than calculating densities sort of algorithmically or in a closed form solution, what we do is we generate random variables indirectly from these distributions. And then we use that to typify the posteriors of particular parameters of interest. Gibbs works when you can actually sample directly from the conditional posteriors. So you have to be able to make a conditional random draw from the posterior distribution. Not all distributions like that. Gaussians are really nice in that regard because you can do that. It's really easy to sample from a normal distribution. Other distributions like scalable chi-square are not like that. So you have to do something different. So there's a set of related sampling algorithms called Metropolis, named after the guy who authored the paper in 1953 after it's classified. And Metropolis Hastings, which is a generalization of Metropolis by Hastings in 1970. And this is an algorithm that's used when you can't actually sample randomly directly from the posterior of interest, but you can evaluate if you can actually come up with something that looks like a point from that distribution. So you use kind of a proxy or a surrogate distribution, it's called a proposer or dumping distribution, to make a probabilistic statement that you should